All right, today we're going to dive into something you've probably seen a million times, but maybe never really thought about: the humble whistle. We're going on a little journey here, one of design, spectacular failure, and ultimately discovery, to unpack the wild science behind this simple-looking thing. Let's get into it.
So, seriously, have you ever tried to 3D design one? Or just stopped to wonder how it even makes that incredibly sharp sound? I mean, it looks so simple, right? But as you're about to see, there is a whole world of physics and engineering packed into this tiny little object. At first glance, yeah, it's just a piece of plastic. But turning this idea into a whistle that actually works, well, that's a true tinkerer's journey. It's a surprisingly deep rabbit hole of fluid dynamics, acoustics, and, trust me, a whole lot of trial and error. Okay, so if we're going to build one, we first got to understand how it works. So let's do a little deconstruction. We're going to look at the three critical parts that have to work together perfectly to turn a simple puff of air into a powerful sound. First up, you've got the opening. This is where you blow, obviously. Its whole job is to take your breath and squeeze it into a flat, focused jet of air. Now, the size of this opening is our first big variable. If you get it wrong, say you make it too big, the air isn't focused enough, and you get, well, nothing, just air. Next, that focused stream of air smacks right into this sharp little lip called the edge. Now this is the heart of the whole operation. The edge literally splits the air, forcing it to vibrate, to oscillate like crazy. And that vibration? That's the raw ingredient for sound. No vibration, no whistle. Simple as that. And finally, those vibrations need somewhere to go. They bounce into the chamber. You can think of this as a tiny little concert hall. The chamber takes those raw, messy vibrations, organizes them, amplifies them, and shapes them into a specific, clear frequency. And that frequency is the pitch, the note that you actually hear. So we had the theory, we knew the parts, we fired up the 3D printer and thought, how hard can this possibly be? The answer, it turns out, is very, very hard. And honestly, that's where the real learning and all the fun really started. You know, this Henry Ford quote really nails it. It perfectly captures the spirit of this whole project. Because every single whistle that didn't work wasn't a mistake. It was a clue. It was a data point that taught us something new about the delicate dance of physics going on inside. We started by messing with the opening. And our first dozen or so variations were completely silent. We made the opening way too large, which meant the air pressure was just too low. All we got was the sad little... literally just the sound of air moving through a plastic tube. Not exactly a sports whistle. Okay, on to the next variable, the edge position. So, we tried moving it too far away from the opening. What happened? The stream of air just lost all its focus before it even got there. The result was this really disappointing, airy hiss. Shh. Yeah, we were basically making a fancy salt shaker, not a whistle. Then we started playing with the chamber size. We made it super small, thinking, hey, this will create a really high pitch. And we did get a sound, but it was this pathetic, weak wheeze. It sounded like a mouse with asthma. Each one of these failures, though, taught us just how incredibly delicate the balance is between all these parts.
But after dozens of variations, dozens of 3D prints that gave us nothing but wheezes and hisses and puffs of air, we started to get it. We started to feel the relationships between all the parts. The physics began to click into place, and suddenly we could see a path forward. So we took everything we learned from all of our glorious failures: the perfect opening size, the exact right distance to the edge, the ideal chamber volume, and boom, this is it, our breakthrough. We designed a whistle that not only makes a sharp, clear sound, but we were able to channel the escaping air to spin this tiny built-in turbine. It's a complete testament to the process. Every single failed print was a necessary step to get to this one that actually works. So why does any of this matter, right? Because that process we just went through of tinkering, failing, learning, and finally succeeding, it's not just about whistles. It's the blueprint for how we invent anything. It's a much, much bigger idea. You take that same curiosity and persistence, and it can lead you to create all sorts of things, like these clever little puzzles and keychains and toys you see here. It's all about seeing a challenge and just starting to mess around with possible solutions. That very same mindset can create beautiful, complex, geometric art, or even physical models that help us understand really abstract math concepts, like this elegant 3D printed proof of the Pythagorean theorem. How cool is that?
From a simple whistle, you can scale up to building intricate models of platonic solids or even functional objects like a Haberman sphere. It all starts with that same fundamental willingness to just try something and not be afraid if it doesn't work the first time or the 10th time.
And all of this brings us to the most important part of this whole story, you. Because once you see this process in action, you realize that absolutely everyone is a potential designer, whether you know it yet or not. So think about it like this. Making is just messing about with materials, getting your hands dirty. Tinkering is approaching it all with a playful mindset, being totally open to learning from whatever happens. And engineering, well, that's just the art of taking those lessons to invent and constantly reinvent the world around you. I absolutely love this quote by Alan Kay. It's just so empowering. The best way to predict the future is to invent it. Don't just sit around and wait to see what comes next. Go out and build it yourself, even if you start with something as simple as a little plastic whistle. You see, that simple whistle contains a whole universe of science and math and art. It's really an open invitation for you to find something small, to model it, to tweak it, and to learn from all the ways it doesn't work, until, finally, it does. So the only real question left is, what will you make?